And what Cox, Ross, and Cox, Ingersoll, and Ross, the same Cox as Cox, Ross, Rubinstein. So Cox, Ingersoll, and Ross produced a result that said, once you are able to develop that risk-neutral process, you can solve that differential equation using some advanced tools from stochastic analysis and basically say that the price of every zero coupon bond is the risk-neutral expectation of the price of a zero. And what's R? This is an expectation, and that tells me that what's inside the brackets must be a random variable. Well, capital R is a random variable. It's the discount factor from time capital T to time little t. What is that random variable that I'm taking the expectation of using the risk-neutral process? What does that mean? Well, first of all, E star, as I said, means we're going to use the risk-neutral process for R in order to calculate this. And what is RT? Well, it's basically an integral of the short rate. Now, in general, we're not going to have a form, R of S, that we can integrate. However, we can approximate this integral with a Riemann sum. And we'll do that in a few minutes. Now, the first thing I want to point out is that the Cox-Ingersoll-Ross result is that, going back to that earlier slide, that the price of an option, or the price of a zero coupon bond, is the expected value of e to the minus r. This is different than saying it's e to the minus expected value of r. Not the same. It's saying you must calculate the price using the random discount factors generated by the process, and then calculate the expected value of those prices. And that is not the same as calculating the price at the expected discount factor. And this follows from Jensen's inequality, which is what we'll talk about next, and that is that the equation, as I just said, requires a risk-neutral expectation of bond prices, not a risk-neutral expectation of interest rates. Jensen's inequality says that we have on a formula by the Cox result that the price is an expected value of e to the minus r. Well, e to the minus x is a convex function, and Jensen's inequality says that if you take an expected value of a convex function, that's bigger than the function applied to the expected value. So if I move this expectation from outside the function to inside the function, I get something smaller. So if I define R to be the correct interest rate that comes from the correct price of that zero, Jensen's inequality says that the correct interest rate is smaller than the risk-neutral average of discount rates. So it's very important that when we're pricing bonds, we take risk-neutral expectations. We do averaging of bond prices. We don't do averaging of interest rates. Because Jensen's inequality tells us if you average interest rates, you're going to get an interest rate that's too big. The actual interest rate that's correct for pricing a bond is smaller than that average interest rate.